recording?
Okay.
Okay, so good morning, everybody. Thank you again for coming back. So this is the second part of the lecture by Marco Piva about higher derivatives quantum field theories. So Marco, please, the stage is yours.
Okay, thank you, Claudio. Good morning, everyone. So I can continue from where we left yesterday. Today will be more about gravity. So maybe yesterday was too much general about, well, it was not very general, it was about scalar fields, but I thought it was important. It is important to understand those things to realize some crucial aspects of higher derivative quantum field theories. But now today I want to talk more about gravity. Just one last thing that I want to say that I forgot yesterday. If we have higher derivative theory like those I was discussing yesterday, that we wrote in this form. It's always possible to make perturbative redefinition of fields and introduce auxiliary field. So you can always use auxiliary field plus perturbative field redefinitions. To obtain a two derivative theory with many fields. So this one is a higher derivative field theory with one field, but it will describe many degrees of freedom, as we saw yesterday, because f, this function f has many poles, might have many poles. All of them describe degrees of freedom. And we can recast this action, making these operations, into an action that has only two derivatives and more fields. For example, in general, you can say this. So you can define an action S prime with the n fields, n different fields, such that this action with tilde fields, now I'm going to say what they are. Will give you back the higher derivative action with one field, where this field tilde I, which are function of the first field that I defined, are just the solution of the equation of motion. So if you plug them back, you get the original action. So this is an auxiliary field. This is the first step. You just rewrite everything using auxiliary fields in a way that when you apply the equation of motion of the auxiliary field, you will get the previous action. And then you do a perturbative redefinition, which can be something like this. Or in general, something more, depends on the theory. In gravity, for example, it's more complicated, so maybe more general would be something like this. But anyway, some transformation that mixes this field such that they all get a kinetic term. So in this case, you will get, you will end up with an action with two derivatives and many fields. Where I write it like this. So there is a kinetic term and interaction. And the kinetic term is written in this way. where the mi squared are the poles of f, like we saw yesterday. And this sigma are the signs of the residues. Of each pole. The residue of Fn in P squared equal mi squared. So talking about higher derivatives in the sense that I defined yesterday, so with higher derivative terms in the kinetic, higher derivatives in the kinetic term, which will modify the propagator and introduce additional degrees of freedom, is not so different in considering just two derivative theories. You can map them perturbatively into each other. So what you're really doing when you have higher derivatives is that you're introducing more degrees of freedom, and if you are introducing them through higher derivatives, at least one of them is a ghost. So in the formulation with higher derivatives, you will see that in this way, when you have this action with just one field and many derivatives, renormalizability is improved because the propagator falls off more rapidly in the UV, and this is, you can see it explicitly, but it will introduce some ghosts. In the same way here, you will have maybe it's not obvious that renormalizability is improved, but it is as well. And the point is that there are some signs that has flipped, which are the signs of the kinetic term for these ghosts. And those minus signs that flip can cancel some divergences and make the theory renormalizable. So in this formulation, this with the many auxiliary fields, renormalizability is not manifest, let's say. But of course, both the theories are equivalent and they are both renormalizable, and both contains ghosts. So in this case, maybe it's more explicitly, you can see explicitly that there are ghosts because you have kinetic terms in the action that has a wrong sign. While in the other case, you have to compute the propagator and check the residue for each poles. But these poles are all poles of the same propagator, so maybe it's not manifest the ghost problem, but it's manifest the renormalizability improvement. So this was some additional comment that I want to add, because this is something that you might also do in gravity. I will not show it, but it's common. So let's proceed with Einstein Gravity. So Einstein Gravity described by the Hilbert action. Which is so now I'm considering just pure gravity. So you have an action of the metric G. My conventions are these signs. I'm assuming that you all know general relativity in some way. I will just tell you. So this is the Newton constant.
Can I ask a question?
So, yes.
So is it? Yeah, I'm sorry for I didn't hear it from your last lecture, but is it clear that sigma I has to be a sign, that it doesn't contain any ratios of mass over a scale, for instance?
No, scale, no. You can.
I mean a ratio of masses,
sure.
or ratio of
you
scale.
Can. This is contained in this. So you can, if you want, you can normalize always the fields. So if
there it's okay.
Yeah, you can always reduce this in this form. So in my mind, I included everything in this transformation. Of course, when I do it in practice, usually if I have, I don't know, I have two fields. Typically, you mix them like this, and then you plug them you plug this redefinition in the action, then you realize that maybe there is some coefficient here that is not 1 or -1, and then you just do a redefinition of the field itself. Normalization.
Okay. Thanks.
And so this coupling K has dimension -2. G is the metric. G is the determinant of the metric. So just to clarify the notation, if in case you don't know or don't remember. This is the scalar curvature. R mu is Ricci tensor. These are my definitions, because you can define it in a couple of ways. So of course, when you check papers of gravity, you will find all the signs different from what is your convention. But this is it. And this is the Riemann tensor, which I just write the first part just to fix the signs again. And then there is some similar terms with the flipped signs and indices. And gamma is the Levi-Civita connection. And this is Riemann tensor. So if you want to study this theory as a quantum field theory, you can do that. But quantum field theory deals with scattering amplitude typically, and compute the element of the S matrix using Feynman diagrams. And this is done only in flat spacetime. So what you do is to expand your metric tensor around flat spacetime, and then you consider a spin-2 field, because this is what you get when you do this. So you expand the metric around Minkowski spacetime this way. So h mu is a field now that propagates in flat spacetime. And then you study this theory. This is the theory of this 2-index field, which you will see described. With this action, it will describe a massless spin-2 field. The inverse of the metric appears inside this Lagrangian. It appears here. So because this G mu with the index raised up is the inverse of G mu with the index down. So the component of the inverse of G can be written like this, which means that when you expand around flat spacetime, this is the inverse. So it's this, but then you have something like a geometric series. So you have other terms, infinitely many. And because of these infinitely many terms, you will have infinitely many terms also in the action, because you see that the Riemann tensor schematically is the derivative of the connection plus the connection square. The connection, I didn't write the expression, but connection is G to the -1 derivative G. Again, schematically, of course, there are 3 possible contractions. We should take into account the symmetries of this tensor. But this is just to visually see where these things goes. So you end up with G minus, with the inverse of G here. So we'll have infinitely many terms. So when you write down the action, the expanded action, as a action of a field H, you will get something like this. Schematically, again, don't want to write all the indices. So you have a two derivative term where this triangle delta is the two derivative operator. And then you have interactions of all possible powers of H, and always two derivative or zero if you have the cosmological constant. But in this case, I didn't put it. So there are all derivative interactions. So you have something like the derivative of H squared, derivative of H, derivative of H, and so on. And then all possible powers. This generates infinitely many vertices. So if you want to see it as a quantum field theory, you will have a 3 legs vertex, 4 legs vertex, 5 legs vertex, and so on. This action is also invariant under diffeomorphism, the one written in terms of G. So it has a gauge invariance. This is something analog to gauge invariance in gauge theories. So is invariant. Which means that when you expand around flat spacetime, also H is invariant under a symmetry. There is the expanded version of the invariance under diffeomorphism. And this means that this operator delta 2 is not invertible. This is exactly like in QED or QCD. You have the kinetic term for your gauge field that in this analogy would be H mu. That is not invertible, and you need to introduce gauge fixing, Popov, ghosts, BRST. It's exactly the same procedure. I will not review it all, but it works the same. It just has more indices. And so this delta 2, I didn't write it, but it's a two derivative operator. So this is just to let you know that this how this is done, but not the details. So you just do a procedure. Analog to that of gauge theories. So gauge fixing, Popov ghost, BRST symmetry, and so on. So you can invert this operator in the end using the same tricks that you use when you have gauge invariance. This is a sort of gauge invariance. You can get your propagator. Then when you have your propagator, you already know that you have all of these vertices, and you can just compute the diagrams. So if you see at the trick, at the simple rule that I said yesterday about renormalizing the field and check the dimension of the parameters, this you can see it also in this case. It's similar. It's a similar situation to the 5 to the 6th theory. So here we have this action, which is now expanded sorry, there was this K. Actually, it was also here. And then you have these other powers of H, like H square, dH, and so on. Again, you can have also H, d square, d square. So if you normalize the kinetic term, as I said yesterday, you have to send H mu into K H mu, where it's kappa, not K. And then you get this, which is canonically normalized. But you get this K, which has negative dimension all around in the vertex. So it's a theory with a negative dimension parameter. Which is already a signal that is not renormalizable. But to see it is better to do it explicitly. So this was done in the 70s by Toft and Veltman for the first time. So this works as follows. You can compute Feynman diagrams. We see that we have infinitely many vertices. So one might think that you need to compute infinitely many vertices even at one loop. But this is not the case because we have a gauge invariance, that is the invariance under diffeomorphism. So, for example, if you compute a one loop diagram like this one, you will get a counter term associated to this to cancel this because it's divergent. So I put this 2 to indicate that is a two-legs diagram. And this counter term will be of this form in dimensional regularization, where you have this delta 4 that is now a 4 derivative operator. So you already see that you generate something that is not in the action because in the classical action there are no 4 derivatives. But anyway, you can continue because still you don't know what to do with this because your original action was a functional of G, the metric. Then in principle, you might think that you have to compute also, I don't know, correction to the vertex. This will give you some counter term of this form where you have some operator which act on some powers or to the third power of the field. But the point is that you can prove with some theorems that the counter term has to be gauge invariant. So gamma CT has to be gauge invariant. And a function, you can also prove that it has to be a function of G. So it has to be gauge invariant and a function of G. This means that all these diagrams, if you continue in principle, you can continue and go on forever, must sum up to give something that is covariant, which means that is made with the things that are covariant according to this symmetry. So all these diagrams sum up to give something that can be, that is a function. It has to be a function of G, and it is built as functions of R, G, R mu nu, and so on. So all these quantities that are covariant, and then they have to be Lorentz invariant, there has to be a scalar, so you have to contract them all in all possible ways, and you get these things. So basically, what I want to say with this is that it's enough to compute this to realize that at one loop you have what is the form of your one loop action, which is this one. Sorry, your one loop counter term effective action. Is enough to compute the self-energy, basically, the self-energy of the graviton. Because this will be a function with 4 indices, and it will contain projector that identifies these two terms in a unique way. And then, well, the linearized version of these two terms. Sorry, linearized, I mean, the quadratic. So if you linearized the Riemann, the Ricci tensor, linear, it's something like derivative of h. The same is for R. And so you have the product of two of these. So you have a square of h. It's of order 2 in h, this quantity. And because of gauge invariance, which is diffeomorphism invariance, these are uniquely determined by this. So you can just compute this diagram, which is not so simple to do by hand, unless you develop some technique or you use Mathematica. And you can uniquely determine that this is the form of your one loop action. This was done by Toft and Veltman in, I don't remember the year, but this was from them. Now, in the case of gravity, if it's pure gravity, as we are considering now, this is actually a lucky case because these terms are proportional to the equation of motion of pure gravity. So r squared and r mu nu squared are proportional to the equation of motion. In pure gravity. So equation of motion for our action is the well-known Einstein equations, are the well-known Einstein equations. So in general, why did I say that this is a lucky case? Because when you have terms that are proportional to the equation of motion and are perturbative, these are perturbative because A and B will contain powers of h bar. So they are quantum corrections, so they are small compared to the classical action. You can perturbatively absorb them. This works as follows. If you have an action of a field phi, which is written as an action, another action, S dot, S naught, plus some terms that are proportional to the equation of motion of S0, S naught. And then here there might be some function of phi. Then there exists a field redefinition phi that goes into phi prime, which is a function of phi, such that your action is just the S0 action with the field redefined. This you can simply see by making a Lorentz, a Taylor expansion, because we said that this is again is a perturbative field redefinition. So if you have phi prime, there is phi plus some delta phi, plus higher order. You just do the expansion to check this. So S0 of phi prime is S0 of phi plus delta phi. And then if you do Taylor expansion, you have this plus exactly what you want. So order by order, you have this equality. You just have to fix delta phi. In this case, in this example, if you fix delta phi to f of phi, which was here, then you can show that this is true. With this, then you have found the field redefinition that makes this that absorbed away these terms. And the same is in Einstein Gravity. So in GR, we have a field redefinition of the metric in this case, which has this form. If you plug it into the action and expand, and you get this. So if you fix delta G to be A R mu nu and minus B half G mu nu R, you will get that pure GR is one loop finite. So one might think, okay, good. Now, well, I didn't expect that. No? Maybe the first time they compute this, they thought they have this spot because you have this negative dimension parameter. But all the one loop divergences in pure gravity are proportional to the equation of motion, which means that they are not there. They just disappear with a field redefinition that doesn't affect any physical quantity. While when you have divergences in renormalizable theory, well, in theories that are divergent, we say that these are finite because these divergences can be absorbed with this field redefinition that is of a special kind. It's proportional to the equation of motion. It means that it will not appear in any observable. When you absorb the divergences of a renormalizable theory, which means that, for example, is one loop divergent, and then you need to cancel those divergences, you do a field redefinition as well, but it's of a different kind. It's not a field redefinition which makes use of equations of motion. And this is what you get when you renormalize QED. So you have the running of the constant, coupling constant, which is something that is left from this procedure. So this procedure somehow affects the physics. While when you have field redefinition of this type, this is the same as saying that there are no divergences at one loop. So to check, well, you can continue, but it was very easy to see that this is not true always. So in the same paper of Toft and Veltman that proved this, shown this, they also coupled GR to massless scalar. So you have total action. There is the Hilbert action plus a massless scalar. Then if you compute one loop, the one loop divergences, you will get everything you can compute. Everything you can generate with this with the right dimension. So you have counterterms of this form. Well, first you have the same, something similar, where maybe the A and B are different, but they have the same expression. These now cannot be absorbed anyway, because they are not proportional to the equation of motion, because there is a matter. So the equation of motion involved the energy momentum tensor generated by the presence of matter, and they cannot be absorbed using the equation of motion. You can use the equation of motion to reduce the number of possible terms, but you cannot cancel them, because not all of them are proportional to the equation of motion. Then you have other terms, which contains a higher derivative as well. So this means that Einstein gravity coupled to matter, the simplest possible matter you can think, a massless field, which is not even self-interacting, is not renormalizable, because it generates terms that are not present in the original action, like this one. Of course, is non-renormalizable in the sense I wanted to stress yesterday. You can cancel these divergences. You just have to add all of these terms in the original action. If you do that and you restart, consider that they are small, so they are perturbative. Then you generate more and more and more. But we will see how you can stop this in gravity. I want also to mention some other computation that has been done to finally declare that GR is not renormalizable. So one can think that maybe pure GR is always renormalizable, and it's not when you couple, or it's finite, but it's not when you couple to matter. So maybe the problem is coupling to matter. No, it's not, because it was computed by Gorov and Sagnotti. The two-loop counter term, which is using some symmetry of the Riemann tensor and invariance under diffeomorphism, is just one. And it is proportional to Riemann cube. So there is some constant. This is the Riemann tensor. So it's the trace of the cube of Riemann tensor. That I will denote like this. So this definitely concludes that GR is not renormalizable. There are some other things that one might try to do. One is to increase the number of space-time dimension. For example, but this is not good. For example, in 6 space-time dimension, you will get already at one loop. This counter term with the Riemann cube. you can think to use supersymmetry. N equal 1 supergravity is 2-loop finite. But then from 3-loop is divergent and non-renormalizable. I don't know what's the situation with higher n. When I was making my master thesis, I remember that I didn't find anything about n equal 8. Well, people claim that n equal 8 might be finite to all order, but I think there is still no proof of this, or maybe there is even this proof. So one way to proceed, this was just to mention some possibilities. One way to proceed is to then just include all of them, as I said. Non-renormalizable, it doesn't mean that some physical quantity is really divergent. The only divergent problem is that you have infinite number of coupling that you need to fully determine, to fully predict your observables, to extract prediction. But one can say, okay, this is it. Nature is like this. Everything other than gravity is described by renormalizable theories. So you have just a finite number of parameters that you have to fix with your experiment. And in gravity, you cannot. So you can just surrender and study this theory. And so you have the classical action of quantum gravity that can be written. Well, we already know that, for example, in pure gravity, we have, you can use this property that some terms are proportional to the equation of motion, so we don't need to include them. Then you can just write all of them. This is in the case of pure gravity. Because everything that can be generated will be generated by loop diagrams. So you just add everything up to this field redefinition that involves the equation of motion. So you start from the Riemann cube, and then you might think to add everything else you can construct. So some function of covariant derivative and Riemann tensor contracted in all the possible way. And then you might think to study this theory. Of course, the more you want to go to high energy, the more you need to know many parameters here, all this lambda. You might be lucky and find some observable that depends on only a finite subset of this lambda, but I don't know. I didn't study too much in this direction, so I don't know what I can say, but this is one possibility, because this theory would be unitary. You will have all of these terms which are considered perturbative compared to the Einstein-Hilbert action. So all this lambda contains powers of h bar, but you include them already in the classical action with the right constant to cancel the divergent terms. And then you can study this theory, but this is not what I do. So I just want to mention this possibility. I think now is good time to make a break, and in the next part I will talk about higher derivative quantum gravity and how to define them in a good way.
Okay, so let's make a 5-minute break, and so we can resume at 53. And if you have any questions, this is a good time to ask.
Can I make a question or a comment?
Mm-hmm.
So I think in the literature there's mention that there's an exception of there's a renormalizable gravity which is conformal, so with 4 derivative terms, but it has
yeah, this is what I'm gonna talk about after.
Okay, sorry.
But that's because so far I didn't want to introduce higher derivative terms. So in here I don't have them.
Okay.
That's what you get if you want to renormalize. It's not not only the conformal one, also a non-conformal version is renormalizable.
I see. Okay.
Yeah, this is what I'm gonna talk in after the break.
Okay. Sorry.
Yeah, no
Thanks.
problem. Now I change a little bit the convention for the parameters. So now K is dimensionless, kappa, sorry. Gamma has dimension 2, and alpha and beta has dimension 0. This is a bit redundant to include both alpha, beta, gamma, and kappa, but I do that just by convention, so I always write it like this, because then kappa being in front of everything will count the powers of sorry, the loop order, the number of loop. It's like h bar when you have h bar. If you reinstate h bar in your action, in the path integral would be something like this with h bar. So 1 over h bar on the action, and h bar counts the number of loops. So I keep k usually to leave the number of loop visible when I compute counter terms, but this is just to tell you. So this theory is renormalizable. So maybe you might be confused because I said before that these terms are proportional to the equation of motion of this action. Actually, they are proportional to the equation of motion without the cosmological constant. So I can absorb them with a redefinition, but that redefinition was perturbative. So this means that you can do this only when alpha and beta are considered like quantum correction. They have h bar, powers of h bar. In this case, alpha and beta are just parameter, and they can be, they are just independent parameter, and they are there. And you are defining your classical action with this parameter in it, and these additional terms in it. And this is completely different. You define a completely different theory. If you have a theory with this classical action plus some quantum correction, which would be, this would be the full one loop classical action, sorry, the one loop effective action, the local part in Einstein Gravity would be like this. Then this term can be absorbed away with those perturbative redefinitions. But in this case, you are defining the theory, classical theory, like this. So alpha and beta are not quantum corrections, are not numbers that arise from quantum correction, they are there. And this is a good thing that you compute the one loop divergences, you get this r square and r mu square, and then if you say, okay, but let me try to add them directly in the classical action and start your analysis from scratch, you get that counter terms are closed under normalizability. This is slightly different from phi to the sixth, as we saw yesterday. So I said before that Einstein Gravity in some respect resembles the phi to the sixth theory problem, that is not normalizable. But in that case, with the phi to the sixth theory, you can generate a phi to the eighth at one loop. Then if you put it in the action with the phi to the eighth, you can generate a phi to the 12th. And it's never ending. In this case, Einstein Gravity generates an r square and r mu square. But if you continue, you generate Riemann cube and so on. But if you put the first one loop counter terms in the action, the classical one, and then you start again, then it will be closed, which means that the counter terms at every loop order will have the same form of the classical action. So you have this. And this is true for every n, which is the number of loops. This was shown in 77 by Stella. To show this, as I mentioned yesterday, again, this is, I don't have the time for this, if we wanted to talk about higher derivative in general. but since you have a gauge invariance in this theory, which is the invariance under diffeomorphisms, you will introduce, you will have your physical field, you will have a ghost, you will have an anti-ghost, you will have a Lagrange multiplier in analog way, if you know these things, in an analog way as in QCD. And to prove this, you have to show that the counter terms will not contain all these terms. This is not trivial. And it was a conjecture for, it was proven for any non-abelian gauge field, but it was not proven until a few years ago in general for gravity. It was, in this case, was a, in this paper, he mentioned this and he said this is a conjecture. So he assumes that at some point, but the proof it's basically it's already in this paper. Besides these subtleties, that to show that these are not in the counter terms, you have to prove this conjecture. Or you can do it in a specific gauge, if I recall correctly, which is what Stella does, but I'm not entirely sure that was like this. But anyway, so this is a good viable theory because it's renormalizable. By the way, it resembles somehow, this is a, if you want, a curiosity, but it resembles somehow Young-Mills, because the Riemann tensor, for those you don't know, is given by the commutator of two covariant derivative if you apply it to a vector. So if you have something like this, okay, maybe I don't want to make mistakes with the indices, but it should be something like this. So this is similar to QCD. So the commutator of two covariant derivatives gives you F mu. And because geometrically they are the same. They are the curvature of a connection. So in this case, the connection is A mu. In gravity, the connection is called connection. Also in this case. So from the geometric point of view, F mu and R mu nu rho sigma are the same quantity, with the exception that in the case of well, the same quantity, they have the same meaning, but they are in different. This is the technical term is fiber bundle. This is slightly different, the structure, the mathematical structure for this. But if you want, you can see them as a similar object. The only thing is that this has only two indices, so and is antisymmetric, so you cannot define the trace. Well, you can, but it's zero. And in this case, you will have a trace, which is R. You also can contract in some other ways the indices, and you have R mu nu, and then you can have Riemann. And then basically this action is F mu nu, F mu nu. But since there is also the trace, you also have the trace. We don't include the Riemann cube, which would be, sorry, not cube, Riemann square. So this term, because we assume, I assume, that we have the Gauss-Bonnet term, which vanishes. So the Gauss-Bonnet term is this combination. Where is it? I don't remember it. Ah, okay. And this, because of the Gauss-Bonnet theorem in differential geometry, this tells you that, gives you that this is a total derivative of something. So if your spacetime doesn't have boundaries, or the spacetime goes to flat spacetime at infinity, or goes to zero, whatever, with the correct boundary condition that is usually assumed in quantum field theory, this is zero. All the total derivatives are zero. So you can write the Riemann square in as a combination of Ricci squared and R squared. So this is already included here. It's just a redefinition of alpha and beta. So that's why there is no Riemann cube. Okay. So we can reparameterize this action. This is what I usually do because it shows in a more explicit way what are the degrees of freedom once you compute the propagator around flat spacetime. So keeping in mind that this is 0 and also using another identity, which is this one. Where this C is the Weil tensor. Which, if you want, is the Riemann tensor with without all the traces. Let me write this. We can rewrite this action instead of, so we don't need the Riemann square because of this Gauss-Bonnet relation. This is also up to a total derivative, which is 0 in most of the application. So for me, it's an equality, this. So we don't need to include the Riemann, and then we can also re-express the Ricci squared in terms of this Weil and R squared. So instead of Ricci and R, you use Weil and R. And you can rewrite the action in this way. This is completely equivalent. Why do I do this? I do this because when you then compute the propagator around flat spacetime, so again, you write G mu nu around flat spacetime, and you compute the propagator for H mu nu. If you have rewritten everything in this way, you will see much clearly all the degrees of freedom separated in a easier way. So without making any steps to do that, I just show you the result. The propagator for H mu nu is this in momentum space. And using the Feynman prescription. I will tell you what these things are. Plus some gauge fixing term that I'm not going to write. So the reason why I choose this parameterization with Weil and R is because then the parameter in front of Weil square, alpha, will appear alone in this this denominator, and the beta will appear alone in this denominator. Otherwise, they are mixed up a bit. So this is a better way to see the propagator. And these pi are projectors, spin-2 projectors. So a spin-2 contains a spin-2, pure spin-2, spin-1, spin-0, and this project onto the sub-multiplet, if you want. The better way to see this So you see, first you see that this is a higher derivative propagator because you have a p square here and p square here. So when p square is large, this goes as 1 over p to the fourth. So there is a signal that the theory, the renormalizability of the theory is improved. But again, as I mentioned above, you have to prove carefully all the stuff that Stella did in his paper. But anyway, you see that this propagator falls off as 1 over p to the fourth, so it's a higher derivative theory. You have many poles, but they are all separated with multiplicity 1. I mean, so there is a massless pole, there is a massive pole, another massive pole. As I mentioned yesterday, when you have a higher derivative propagator, you can always decompose it as a sum of simple fractions. So let me rewrite this propagator in a better form. Okay, so in this, writing this, the propagator in this way, you can clearly see all the degrees of freedom. This projector, this combination of projectors is the same as in Einstein theory. So this is the projector to massless spin 2. So this gives you a massless spin 2. Which is the gravity. Exactly as in Einstein theory. So Einstein theory around flat spacetime has propagator without this term. So this is the same. So you can already recognize that this theory will contain a graviton, as it should be, but it will contain also these other degrees of freedom. This one is a massive spin 2. So this has 2 degrees of freedom, like the 2 polarization of the graviton, similar in a similar way to the photon case. Or if you know some gravitational waves, that's the same. These are the same degrees of freedom, the 2 polarizations. This is a massive spin 2, which mass squared gamma over alpha, and these are 5 degrees of freedom. And this is a scalar, massive scalar, with mass squared equal to gamma beta over beta, and it's of course is a 1 degrees of freedom. So in total you have 8 degrees of freedom in this theory. And you see that there is a problem here, which is this minus sign. So if you compute the residue of this of the propagator on this pole, you will find a negative residue. And this is what breaks unitarity in this theory. So this is a massive spin 2 ghost. And the spin 2 ghost violates unitarity. For the reason that I have shown you yesterday. So in the end, all of this, I want to stress this because it will be important later, all of these are prescribed with the final prescription. So this theory is renormalizable. So it has only a finite number of parameters, and you need to fix only a finite number of parameters to have your predictions. The problem is that it violates unitarity. and if you violate unitarity, you don't have any probabilistic interpretation, so you don't have any quantum theory. Well, it's a quantum theory in the sense that you quantize things with the usual method and you compute things, but then those things has no sense because you have negative probability or the probability doesn't sum up. You can rewrite this in every possible way. There will be always something that goes bad. You can have negative probability. You can rewrite this change of variables, doing whatever you want. You will have probability that doesn't sum up. If you have probability that sums up, you have instabilities, which means that, for example, the threshold that you have for a process to appear in quantum field theory, for example, you suppose you have a particle which might decay into particle. The momentum of this particle has to satisfy this threshold if you want. Let's say this is m1 and this has mass m2. This has to be m1 plus m2 squared. This is a kinematical threshold for this decay to appear. In theories with ghosts like this one, you will have this, but negative probability. You can exchange negative probability for instability. So you will have this with a minus. This means that you can have 1 GeV particle that decays into 10 to the 9 GeV particle and 10 to the 9 GeV particle minus 1 GeV or minus 2, whatever. This is, of course, absurd. So there is no way to fix this theory. It has the good property of being renormalizable, though. So it's a good arena to study and trying to develop some new ideas. And we will see later today what we proposed a few years ago about this theory. But let's see also some other alternatives because they are related to this proposal that I want to show you, which is related to my research. Okay, so this theory has 4 derivatives because you have 2 derivatives here and 2 derivatives here. So in the equation of motion, you will have 4 derivatives. Or so you just have to sum them, to count them, and there are 4. One might think to add even more higher derivatives and see what happens. Well, we already know from the general argument from yesterday that having more and more derivatives just introduces more and more degrees of freedom, and at least one of them will be a ghost. So you cannot fix this unitarity problem, but they will have some additional properties, so I think it's worth to talk about them, and they are also the starting point for a solution of this problem. So what about more higher derivatives, more derivatives? You can write a more general action of quantum gravity. So first part is the same, and then you write this. Where Pn and Qn are 2 polynomials of degree n. And this nabla square is the covariant derivative square, covariant D'Alembert. And lambda is some scale. So you can just plug there a polynomial of the derivative. You will have a propagator which falls off even more rapidly than the theory that I explained before, than Stella theory. And they will be even more than renormalizable. They will be super renormalizable. This means the following. So of course, this is true for n. So if you have n equals 0, p and q are constant, so you get the previous theory. If n is bigger than 0, these theories are all renormalizable, super renormalizable. Which means that Feynman diagrams are divergent up to a finite number of loops. So in a renormalizable theory, you have the counter term has the same functional expression of your classical action. So you have only a finite number of parameters, but this finite number of parameters will get correction from every loop. So you have infinite smaller corrections to your parameters. In a super renormalizable theory, they will get a finite number of corrections. So at some point after some loop order, there won't be any divergent diagram anymore. And the classification in this case with this theory of gravity, these theories of gravity, you have this. If n is 1, you have divergences up to 3 loops. If you have n equal 2, you have divergences up to 2 loops. And for n equal or bigger than 3, you have divergences up to 1 loop. There is no way to cancel, to avoid this and get 0 loop just by adding more and more higher derivative terms. So the 1 loop divergences will be always there, at least if your degree is high enough, the degree of your polynomials is high enough, you will have only 1 loop divergences, but you cannot cancel them just by increasing n. If you want, you can make this theory finite anyway, because you have only 1 loop. For example, let's suppose you are in this case, you have only 1 loop divergences, so only a finite number of diagrams and only at 1 loop will be divergent. And you can introduce terms which are not kinetic terms, which do not contribute in the kinetic terms and contribute to the potential, let's say, if we can call it like this. For example, terms which are cubic in the curvatures. So you can add something like this, which has this form. Sorry, cube. Well, all the possible cubic term will make the game. Because these quantities will not run. A1, A2, they will not get any loop correction. Because since the theory is renormalizable, well, super renormalizable, but in particular renormalizable, it means that you cannot have higher and higher derivative terms in your counter terms. The counter terms of this theory, of all these theories, have all the same expression, the same functional form, sorry, as this theory, as the Stella theory. So all the counter terms also in this case have this form. There is nothing with more derivative there, even though the classical action has this, might have these terms like R box R, R mu nu box R mu nu, or box square, box cube, whatever. The counter terms will always be of this form. And they will be there only at 1 loop if n is at least 3. And this will not get any correction, so you can just fix them to cancel the 1 loop, and then you have a finite theory. Okay, this is just a theoretical game that you might think it might be useful to play with this because you have a finite theory. So it's even better than being super renormalizable. But again, because of these kinetic terms, you have ghosts, many ghosts. But why I wanted to mention this? So we had only one ghost, now we have many. So I just made the unitarity problem even worse. I want to mention this because there is a class of these theories which has some peculiarity, and this is where I started to study my part of my research during the PhD. There is a special subclass of this theory, which is the subclass where P and Q have complex conjugated pairs of poles. So for example, again, it's easy to just use a scalar propagator because all of this has to do with the poles. The poles doesn't care about what's in the numerator or what's the tensorial structure of your propagator. So I just write a scalar propagator to make you understand. In the case of gravity, there will be just a tensor that multiplies this and some gauge fixing term. But this complex conjugated poles means that you have the scalar part of the propagator, if you want, which is the one that encodes all the poles. It's something like this. So if you look at the poles in the P0 plane, so P squared is P0 squared minus P squared. If you look at the complex plane of P0, you will have two poles which are shifted with the Feynman prescriptions, which are the two usual massive poles that are slightly shifted from the real axis by the prescription. And then you have additional poles which comes in complex conjugated pairs. Why is this interesting? Because these two poles, the one with the Feynman prescription, do not give any problems. They are real poles, except for this tiny I epsilon. They all have, they both have positive residue, so they do not ruin unitarity in any way. The problem comes with the additional poles because some of them has negative residue, but they appear in composite conjugated pairs. And since, if you remember, the unitarity equation involves the imaginary part of the amplitude, there was some hope that maybe coming in complex conjugated pairs, somehow they will not contribute in any imaginary part, but only in the real part. And if it's the case, then the imaginary part contribution will be given only by this one, and you might preserve unitarity. So I want to start from in anti-chronological order with this, because it makes understand better maybe. So this is a good, another good arena to start from, where you can start to think about new ideas, because you might save unitarity with these complex conjugated pairs of poles. This was introduced by Lee and Vick in the 60s, 69. Sorry, 69. But let me first say something. Usually, you don't have these poles. You only have these two poles that are there. They are located there because of the Feynman prescription. So this quadrant and this quadrant are free of any singularity. And this is the reason, strictly, roughly speaking, this is the reason why a Minkowski theory is equivalent to the Euclidean one. And you can do the weak rotation back and forth. The weak rotation will rotate in this direction. You can define your theory in the Euclidean axis, which is this one, in the Euclidean spacetime, which means that you are on this axis, and then rotate. You will see that if otherwise you define from the beginning your theory in this axis, this is the same, because you can rotate without encounter any singularity. Basically, it means that if you do the residue theorem, if you want to integrate this on this axis, your loop integral, you can close here and you will get this pole. If you are on Minkowski, you can close like this and you will get this pole. You will not get any difference. So the two theories, the Euclidean one and the Minkowski one, are analytically connected. And that's why you can freely move from Euclidean theory or Minkowski theory when you are in a situation, which is the most common one, where you have two derivatives and the poles are shifted in this way. So these two quadrants are free of any pole. The problem is that in this case, we have these complex conjugated pairs of poles. This means that the Euclidean theory is not analytically equivalent, connected with the Minkowski one. So the Euclidean will be different from the Minkowski one theory. Physically different. They will give different results. You can see it, okay, of course, when you have a loop diagram, you don't have just one propagator. So I'm just showing you the pose of one propagator, but this is just to give you the idea. If you integrate on this axis, you will get this pole and this pole and this pole. If you integrate on the Euclidean axis, or the other way, the other three, if you close below, but that gives the same result. If you integrate here, you will have this pole again, but this pole. So this gives a huge difference. And it was shown recently, a few years ago, that the Minkowski theories, any Minkowski theory that has poles in the first and in the third quadrant, so you cannot do the analytical weak rotation, will have all sorts of problems. So Minkowski theories will have non-local counter terms, well, non-local divergences, non-Hermitian divergences, they violate unitarity. All of this violates unitarity because they have these ghosts that I mentioned. And they also violate stability in a similar way that I described above with the two thresholds with the minus sign, stability. This was shown by Aglietti and Anselmi in 2016, I think. All these problems were, except for unitarity, all these problems disappear in the Euclidean. And this, especially these non-local and non-Hermitian divergences. Non-local and non-Hermitian divergences basically means that divergent part of a diagram like this will be proportional to 1 over p squared, the divergent part. And then it might have something like A plus IB, which violate Hermitianicity and locality of counterterms, because in coordinate space, this will be something like 1 over box. So this is the worst you can get in a theory. And all of this problem appears because if you integrate in this axis, you take the wrong pairs of pole. The right pairs of pole, the complex conjugated ones, will cancel the non-local terms in the divergent part, the non-Hermitian term in the divergent part, and they will not be unstable. There will still be the question of unitarity because the residues will be still there. But that's what we have done to solve this problem. So, but first I want to say what Lee and Vic proposed, because this is related to the solution. Lee and Vic said, okay, they somehow realized, even though it was not so explicit like it was done in this paper later, that you have to define the theory in a different way. So they start from the Euclidean and then rotate. And they propose a way to rotate because they realize that, of course, you will encounter this pause if you try to rotate in the usual analytic way, and you will not find equivalent theories, as I mentioned. So their proposal was to modify the contour integration and to rotate basically like this. Usually you have the pause here. The Feynman prescription tells you that this has to stay above and this has to stay below. And then they say, well, let's do the same with the complex conjugated pairs, even if their distance is not infinitesimal, like in these ones that are prescribed with the Feynman prescription. So they propose to modify the contour integration like this. The problem with this is that this way of defining the rotation is inconsistent. This is, again, the P0 plane. And then some of the inconsistencies are fixed by a prescription. So this was Lee and Vic in '69. And then some other people propose a prescription to avoid problems. I'm not gonna explain all of this because I don't have time, but there are some problems with this rotation. And some other people propose a prescription, which is called Klopp prescription. This comes from Katkowski, Lanshoff, and I don't remember the other two people, sorry. But they claim they fix this using this prescription and they fix all the problems. Although even Lee and Vic realized that if you go to 2 loops or 3 loops, then you might have some inconsistencies. But then we proved that in 2017 that these Lee-Vic theories with the Klopp prescription are inconsistent. This was in one of my papers with Damiano Selvi. We didn't only point out where are the inconsistencies in this formulation, we also show how to fix it. To fix this, basically you have to do something very similar to this. This was only in the P0 complex plane. You have to do an analog thing also in the space momenta 3-dimensional volume, or D-1 dimensional, if you're doing dimensional regularization. So I don't have much time left, but to sum up, Lee and Vic proposed to the, so Minkowski theories with this type of propagators have this type of integral. So let's say this. Theories with complex conjugated poles have propagators like this. I just don't add the other part. Just these are all. This is a theory with 4 complex conjugated pairs. Well, 4 poles that comes in complex conjugated pairs. So let's say that this is the propagator of your theory. If you want to compute, for example, 1 loop diagram, suppose you have a 5 to the 3rd interaction. So in the Minkowski case, what you have is an integral over k, which is the loop momentum. Then it's just the product of two propagator. The integral over k is on R. The integral over the space momentum is over R3 with the Minkowski signature, of course. And this is the one that gives non-local counter terms, non-Hermitian, and so on. Then there is the Liebig proposal. They say, let's do the same with this type of theories, but instead of having R here, they do their modified contour integration. Let me call it Liebig domain, if you want. But this is still on R3, and this was their mistake. And this is what we call non-analytic weak rotation. You use the Liebig contour, so that was a good idea to start. But you have to use also deformed domain for this integral. And this has to be a special one. So D is a domain that belongs to C3. This has to be a very special one because it has to fix also Lorentz invariant problem, because here you have Lorentz also, I forgot, Lorentz invariance violation. This sounds a bit complicated. We did some explicit example. You can somehow make a recipe to fix, to find D, but basically you have to find the specific domain for every diagram. The recipe for the Liebig one is clear. You have to keep the poles, complex conjugated pairs always above and always below this, the one on the right and the one on the left for each propagator in every diagram. But the recipe for this is a bit more complicated. But what we have shown in this paper was that all of this procedure is equivalent. This is equivalent to use the average continuation. What is this? Usually, when you have, now I'm going to tell you this and then I finish. When you have a propagator in a standard theory, so now let's forget about higher derivative theories. You have this thing. This is not a good distribution. You have to define it as a distribution. So you have to give a prescription. Choosing a prescription for the propagator and then using this propagator with all the Feynman rules and perturbative techniques to get an amplitude. But usually you use this propagator, you get an amplitude. The amplitude can be viewed as a function of p squared. Let's suppose that this is a one loop amplitude, p squared in C as a complex function. And this function will have some branch points. When a complex function has a branch cut and branch cuts and branch point, you have also to give some prescription because otherwise it's not uniquely defined. The way you define the propagator is directly connected to the way you define this complex function, and you say how to circumvent the branch cut. What is usually done is to use the Feynman prescription. If you use the Feynman prescription, then you have, let's say that this is the complex plane in P0. Now P0 is the external momentum. And the amplitude usually have branch points like this and branch cuts. You have to say what to do when you want to go on real values. So you want to go here on the real axis. if the propagators, all the propagators that you use to build your amplitude are prescribed with the Feynman prescription, this means that you go from above on this side and from below on this side. Below, above and below the branch cut. This is the weak rotation. And this is how you define your amplitude that I'm gonna call A+, which means that it has P squared plus I epsilon. The average continuation, which is what I was mentioning here, which is what we proved to be equivalent to do all of these very complicated deformations, but it's doable and it gives unique, non-ambiguous Lorentz invariant amplitude. So once I can generate amplitude given a theory, even with some weird method, I'm fine. I will generate amplitude, I will generate probabilities, unitarity is safe. That's what we also proved. That in this way you don't violate unitarity. That was the main important thing to say. I have Lorentz invariant amplitude, unitarity is satisfied, then I just make prediction and check this prediction. It's a well-defined way to have a theory. The average continuation is what I called AB, average. And this is just the average between this A plus and what I call A minus, which is just the other way around. So going from below and above, so the opposite way. So you just do the average with each cut. If you do this, in the case of these theories, with this complex conjugated pairs of poles, unitarity will be okay, will not be violated. This will be equivalent to do all this weird stuff here. Lorentz invariance is not violated. And unitarity, I said unitarity is not violated, but this is not violated only in the subspace of your Fock space, if you remember what I was saying yesterday. Only in the subspace of your states that do not, that are not these ones. So if your theory also contains standard degrees of freedom, you quantize that with Feynman. Then you can separate with simple fraction, as I told you. You can have something like this times some factor. This is prescribed with Feynman prescription, while this is defined with this amplitude. So every time there is a branch cut that will generate these particles, you use this. Every time there is a branch cut, because the branch cut are associated to the physical production of particles, of degrees of freedom associated to these poles. So for the Feynman degrees of freedom, the one that you want to generate, let's say, you use the Feynman prescription. For these ones, if you use this prescription, then you can project onto the subspace where they do not appear as external state. In that subspace, the theory is unitary. And because of this choice, they will not generate it back. If you remember yesterday, I told you that the problem are the cutting equations. Because the cutting equation tells you that the imaginary part of some diagram minus I is equal to the sum over the cuts, all possible cuts, which is almost like the unitarity equation. The problem, yesterday I told you that if you want to turn this, if you collect all the diagrams, you can write it in this way. And then you have this H, which might be negative. You want the unitarity, which is this one with H equal to 1. And I told you, you can project onto a subspace where H is the identity. The problem is that you also have to modify the imaginary part somehow. And then you can get an equality, starting from the cutting equations. This is what modifies the left-hand side of this equation. And so when you do a projection onto a subspace where you know that the S matrix would be unitary, well when you know where that H is the identity, then you also use this rule to modify the imaginary part. Yesterday I told you that this is called a consistent projection. Another consistent projection is the BRST invariance, because in that case you project onto the subspace where there are no longitudinal degrees of freedom or temporal, in the case of gauge fields. And on the left-hand side, what changes is that you add additional diagrams that involve the Popov ghost, and those will cancel the weird behavior of the non-physical degrees of freedom. In this case, there is just another way to cancel the weird behavior, and this way is to use this analytic continuation for these degrees of freedom. Now, the best part in this, and then I conclude, is that this formula doesn't really care if your theory is a higher derivative one or not. It doesn't care if your pose comes in complex conjugated pairs or not. So you can apply this formula to whatever degrees of freedom you like, because it doesn't depend on M if you want. So if you can apply this to any theory and to any degrees of freedom you like. You can even have a theory which is already unitary, but you want a funny theory where some degrees of freedom are projected away, and you can apply this to that. Of course, the main application to me is to apply this to the Stella theory, which was the one like this. The problem of this one is that this theory has ghost. The ghost is there because of this term, but they do not come in complex conjugated pairs. So the idea of having some cancellation between complex conjugated pairs will not work here. But it doesn't work anyway. The only way to make it work is to use this average continuation. But this average continuation, in the end, doesn't really care if they are complex conjugated or not. It just says that if you use that, you will have a well-defined theory, you will have a well-defined set of amplitudes, Lorentz invariant. They are different if you use this prescription or if you use the Feynman one, so you have physically different amplitudes, and you can apply that to every theory. So you will apply it to this one. And in the end, you can turn this theory into a renormalizable theory. Well, it was already renormalizable, and into a renormalizable and unitary theory. Of course, it's unitary in the subspace where this massive spin 2 associated to this degree of freedom, to this term, do not appear as external state. You can do a consistent projection, and then you will have graviton, which is related to this term, and a massive scalar, which is not a ghost if you choose this sign. It's not a ghost and it's not a tachyon if you use that sign. So in the end, you will have a theory which starts from this unprojected action. Then you project it using this prescription, and then you will have unitarity in the projected subspace. So this is a way to have a unitary and renormalizable theory. Renormalizable because this prescription doesn't affect at all the renormalizability property of this theory. Okay, so I think I said everything I wanted to say.
Okay, thank you, Marco, for being on time for this very interesting lecture. So if there are questions, please just unmute yourself and ask.
So maybe one short question.
Mm-hmm.
So usually we use Feynman prescription to have causality as well, right? So in that prescription, how will causality be preserved? In average or in same?
This is violated only at small scales. So there will be a violation. That's the price that you have to pay. A violation of micro causality. And this is related to the mass. So the scale where this violation appear is related to the mass of this, in this case of the spin 2, this massive spin 2 degrees of freedom. In general, it's related to the mass or to the width, depending on which one is bigger, of the particle that you want to prescribe in this way. However, there are several papers that Anselmi made with, well, himself and with some students to show that there is no way to make this violation propagate to larger scale. So this is really a confined violation. You cannot do boost or transformation to make it look in another reference frame to make it look like you violate causality at the macroscopic scale. Because the only way to do that would be to go to a Lorentz frame where you move at the speed of light, almost. That's the only way, and there is no such thing in the universe. So yes, there will be a violation of causality, but it will be micro violation. And since we don't know basically anything about causality and microscopic scales, that it's a good price to pay.
And now follow-up question to this. So if we couple matter to this theory, let's say, then this micro violation of causality will not penetrate there as well, or?
Yeah, it will be the same.
So there doesn't grow as well.
Yeah, it doesn't go as well. Because that is related only to having choose this for the degree of freedom that you prescribed. So in this case, this massive spin 2 that it's due to this term is the only one that you prescribe with that prescription. And the violation is related only to the fact that you use that. If you couple standard model to this theory, it's totally fine. It will remain the same.
Sure,
the only thing that might change is the scale from on where this happens, which is anyways always suppressed by the mass of this.
Sure. So if we think in terms of effective theory and integrate out those degrees of freedom, effectively it will generate some high dimensional operators in standard model which violate causality, right? And if I understood correctly, your statement is that this violation in the standard model will be again in same scale and will not grow.
Yes.
I see. Thank you.
You're welcome.
Are there any questions? If no, I stop the recording.